The dawn of an era, a nation mobilizes. The morning light filtered through the tall windows of the Oval Office on May 16, 1940, casting long shadows across Franklin Roosevelt's desk. Outside, the cherry blossoms had already fallen from the trees lining the Potomac, their brief beauty replaced by the steady green of early summer. But inside that room, the president's attention was fixed not on the changing seasons, but on a series of photographs spread before him, grainy images from across the Atlantic that would reshape the very foundation of American naval power. The photographs showed German U-boats prowling the shipping lanes, French ports bristling with enemy vessels, the smoking ruins of Rotterdam. Each image told the same story. Europe was falling, and America's two-ocean navy existed largely on paper. Roosevelt leaned back in his chair, the weight of decision settling on his shoulders like a familiar coat. The United States Navy possessed exactly 7 fleet carriers. 7. To protect 2 vast oceans, to project power across the Pacific's endless expanse, to safeguard the Atlantic lifelines that kept Britain alive. It wasn't nearly enough. What Roosevelt was about to set in motion that morning would become one of the most ambitious industrial undertakings in human history. Not just the building of ships, but the creation of floating cities, each one capable of carrying nearly 3,000 souls into battle. The Essex-class aircraft carrier program would demand new technologies, revolutionary construction techniques, and a mobilization of American industry that would transform sleepy coastal towns into roaring centers of maritime power. But first, there was the question of whether it could even be done. Admiral Harold Stark, Chief of Naval Operations, had arrived early that morning with a folder thick enough to serve as a doorstop. Inside were the preliminary studies, the cost estimates, the timeline projections that would either launch America toward naval supremacy or reveal the impossible nature of the task ahead. Stark was a methodical man, given to careful analysis rather than bold pronouncements. When he spoke of building 24 new fleet carriers, his voice carried the weight of someone who understood exactly what those numbers meant. 24 carriers, each one 872 feet long, longer than 2.5 football fields laid end to end. Each one requiring 21,000 tons of steel, enough to build a small skyscraper. Each one demanding precision engineering that would make a Swiss watchmaker weep with envy, because unlike a building or a bridge, these floating airfields would need to survive typhoons, enemy bombs, and the crushing stresses of launching aircraft in 30-foot seas. The mathematics alone were staggering. If you lined up all the steel required for the Essex program, it would stretch from Washington, D.C. to Philadelphia. The electrical wiring needed would circle the Earth's equator twice. The rivets, millions upon millions of rivets, would weigh more than the Statue of Liberty. And all of this would need to happen while German submarines prowled ever closer to American shores, while the Japanese Navy grew stronger in the Pacific, while time itself became the most precious commodity in the American arsenal. Roosevelt understood the enormity of what lay ahead, but he also grasped something that his advisors were only beginning to appreciate. This wasn't simply about building ships. It was about building an entirely new kind of naval warfare, one where the aircraft carrier would replace the battleship as the ultimate expression of sea power. The Essex class wouldn't just be bigger than their predecessors. They would be fundamentally different, designed from the keel up to launch more aircraft, faster and more efficiently than any carrier ever conceived. The planning had actually begun months earlier in the sterile conference rooms of the Bureau of Ships. Naval architects had gathered around drafting tables covered with blueprints, their slide rules clicking like castanets as they calculated load distributions and center of gravity equations. The challenge wasn't just making the ships bigger, it was making them better. The previous generation of carriers had revealed crucial flaws under the stress of combat operations. Flight decks that couldn't handle the weight of new, heavier aircraft. Hangar spaces too cramped for efficient maintenance. Fuel systems that turned the ships into floating bombs when enemy shells found their mark. Captain John McCain, grandfather of the future senator, had submitted a report after observing carrier operations in the Atlantic. His recommendations read like a wish list from naval aviators who had learned hard lessons about what worked and what didn't when the shooting started. Longer flight decks for safer landings, better armor around the aviation fuel storage, improved radar systems that could track incoming aircraft at greater distances. Each improvement seemed modest on paper, but collectively they demanded a complete rethinking of carrier design. The Essex class would incorporate lessons that hadn't even been learned yet, because the naval architects understood that these ships would still be fighting battles 20 years in the future. They were designing not just for the war that was coming, but for conflicts that existed only in the imagination of strategic planners. This meant building in adaptability, spaces that could be reconfigured, systems that could be upgraded, structures strong enough to support weapons that hadn't been invented yet. But before the first rivet could be driven, before the first steel plate could be cut, there was the question of where these maritime giants would actually be built. America's shipyards in 1940 were geared toward merchant vessels and smaller warships. Building a fleet carrier required dry docks of unprecedented size, cranes capable of lifting sections weighing hundreds of tons, and most critically, workers who understood the intricate dance of naval construction. Newport News Shipbuilding in Virginia emerged as the natural choice for the lead ships. The yard had experience with large naval vessels, and more importantly, it had the infrastructure to handle the Essex class's massive dimensions. But even Newport News would need to expand, to dig deeper dry docks and install more powerful cranes. The Fore River Shipyard in Massachusetts would join the program, as would the New York Shipbuilding Corporation in Camden, New Jersey. Each yard would need to learn the Essex design, train their workers in new techniques, and somehow compress what normally took 4 years into a construction timeline measured in months. The urgency was palpable in every planning meeting, every design review, every budget discussion. Intelligence reports from Europe painted an increasingly grim picture of German naval strength. The Kriegsmarine was launching new U-boats at an alarming rate, and their surface raiders were wreaking havoc on Allied shipping. In the Pacific, Japanese naval aviation had demonstrated capabilities that sent chills through American strategic planners. The attack on Pearl Harbor was still more than a year away, but perceptive observers could already see the storm clouds gathering across both oceans. Roosevelt's naval expansion program faced skepticism from multiple quarters. Isolationists in Congress questioned the need for such massive expenditure when America wasn't even at war. Budget hawks worried about the program's astronomical costs. Each Essex-class carrier would cost roughly $45 million, equivalent to nearly $1 billion in today's currency. Naval traditionalists argued that battleships remained the ultimate expression of sea power, that aircraft carriers were useful auxiliaries but couldn't stand in the line of battle against enemy dreadnoughts. But Roosevelt had studied the early reports from the war in Europe, and he understood what many of his contemporaries missed. Naval aviation wasn't just changing how wars were fought at sea, it was changing the fundamental nature of naval power itself. The carrier that could launch strikes against enemy ships beyond the range of their guns would dominate the ocean battlefields of the future. The Essex-class program wasn't just about building more ships, it was about building the right ships for a new kind of warfare. The president also grasped the industrial implications of the program. Building 24 fleet carriers would require a mobilization of American manufacturing capability that would transform the nation's economy. Steel mills would need to expand production. Electronics companies would develop new radar and communication systems. Aircraft manufacturers would design planes specifically for carrier operations. The ripple effects would touch every corner of American industry, creating jobs, driving innovation, and preparing the nation's industrial base for the larger conflict that seemed increasingly inevitable. In the quiet of that May morning, as Roosevelt signed the authorization that would launch the Essex program, he was setting in motion forces that would reshape not just the Navy, but America itself. The sleepy coastal communities that housed the shipyards would soon boom with workers drawn from across the nation. Farmers from the Midwest would learn to weld steel. College graduates would master the intricacies of naval architecture. Women would enter the workforce in unprecedented numbers, their skilled hands guiding the construction of the most complex machines ever built. The Essex-class carriers would become symbols of American industrial might, but they began as numbers on a spreadsheet, lines on a blueprint, and the bold vision of leaders who understood that the future of American security lay not in the fortifications of the past, but in the mobile airfields that could project power across the vast expanses of the world's oceans. As the morning sun climbed higher over Washington, casting new shadows across the Oval Office, the great work was about to begin. From molten steel to riveted hulls. As the morning sun climbed higher over Washington, casting new shadows across the Oval Office, the great work was about to begin. But first, the raw materials of war had to be forged from the earth itself. In the blast furnaces of Pennsylvania and Ohio, temperatures soared beyond 2,000 degrees Fahrenheit. The very air shimmered with heat as iron ore from the Mesabi Range met limestone and coke in a dance as old as civilization itself. But this was no ordinary steel production. This was steel destined for the flight decks of history. The furnace operators, their faces gleaming with sweat despite protective gear, monitored the crucibles with practiced eyes. They could read the color of molten metal like sailors read the sky. The deep orange that spoke of proper carbon content. The brilliant yellow-white that meant the temperature was climbing toward perfection. These men understood that every ton of steel flowing from their furnaces would eventually face Japanese bombs and kamikaze attacks in the far Pacific. At Bethlehem Steel's massive complex, the night shift watched rivers of liquid fire pour into waiting molds. The sound was indescribable, a roaring hiss that seemed to contain the very essence of industrial power. Steam rose in great clouds as the molten steel met the cooler air, creating momentary phantoms in the darkness. Each pour represented weeks of future work, months of construction, years of service in the fleet. The steel plates that emerged from these mills were not merely metal. They were the building blocks of floating cities. Some plates measured 40 feet in length, their surfaces smooth as mirrors, their edges cut with mathematical precision. Quality inspectors moved among them with calipers and gauges, checking thickness tolerances measured in thousandths of an inch. A single imperfection could mean catastrophic failure when a 5-inch shell struck the hull at battle speed. Transportation of these massive plates required its own logistics network. Specially designed railroad cars, their wheels groaning under loads of 30 tons or more, carried the steel eastward to the shipyards. The Pennsylvania Railroad added extra locomotives to handle the unprecedented tonnage. Dispatchers worked around the clock, coordinating steel trains with the precision of military operations. They understood that delays measured in days could extend the war by months. At Newport News Shipbuilding and Dry Dock Company, the steel began its transformation into something far greater than the sum of its parts. The shipyard stretched along the James River like a mechanical city, its skyline dominated by towering cranes and the skeletal frameworks of ships under construction. The morning shift arrived at dawn, their lunch pails and thermoses in hand, ready to continue work that had begun the previous evening and would continue long after they went home. The keel-laying ceremony for each new Essex-class carrier was both ritual and practical necessity. The first steel plate, perfectly positioned according to blueprints that filled entire rooms, was lowered into place with ceremonial precision. But ceremony quickly gave way to the relentless rhythm of construction. Within hours, the first plate was joined by others, creating the backbone upon which everything else would depend. The riveters were artists of industrial warfare. Working in teams of 4, they moved across the growing hull with practiced coordination. The heater tended a portable forge, keeping rivets at precisely the right temperature, hot enough to be malleable, cool enough to handle safely. The catcher positioned each glowing rivet with tongs that had been shaped by decades of experience. The bucker held the backing plate steady while the riveter drove the pneumatic hammer home. The sound of riveting became the heartbeat of American shipbuilding. Rapid-fire bursts echoed across the water as thousands of rivets found their permanent homes. Each rivet was driven with exactly the right force. Too little, and it would fail under stress. Too much, and the surrounding metal would buckle. The experienced riveters could gauge the proper pressure by sound alone, their ears tuned to the precise note that meant a perfect joint. Between the thunderous hammering, other sounds filled the shipyard air. The steady hum of electric welders supplemented the riveting on interior bulkheads. The screech of metal being cut to exact specifications. The rumble of overhead cranes moving massive sections into position. The sharp whistle blasts that coordinated movements across the vast construction area. Together, these sounds created an industrial symphony that spoke of American determination. The men who built these carriers came from every corner of the nation. Farm boys from Iowa learned to read blueprints that covered entire walls. Former automobile workers from Detroit adapted their precision skills to naval architecture. Experienced shipwrights from Maine and California found themselves training newcomers who had never seen the ocean. They worked 10-hour shifts, 6 days a week, understanding that their craftsmanship would determine whether American pilots returned safely from missions thousands of miles away. Quality control reached levels previously unknown in peacetime construction. Navy inspectors, their clipboards filled with detailed checklists, examined every weld, every rivet, every joint. They carried small mirrors on telescoping handles to inspect areas that couldn't be reached directly. They used magnetic particle testing to detect invisible flaws in critical welds. They knew that a single oversight could doom a ship and its crew of 3,000 men. The hull construction proceeded in carefully orchestrated stages. First, the double bottom, a maze of compartments designed to keep the ship afloat even after torpedo damage. Then the main deck structure, engineered to support the enormous weight of aircraft, fuel, ammunition, and the constant stress of flight operations. Each deck was a masterpiece of engineering, its steel beams calculated to distribute loads that would have crushed earlier generations of warships. As the hulls took shape, they began to resemble their final form. The distinctive lines of the Essex class became visible, the long, straight flight deck that would accommodate everything from nimble fighters to massive torpedo bombers. The island superstructure, positioned on the starboard side to maximize deck space for aircraft operations. The massive elevator wells that would lift planes from the hangar deck to the flight deck in less than 30 seconds. The propulsion systems required their own specialized construction teams. The main engines, each weighing hundreds of tons, were lowered into position with millimeter precision. The propeller shafts, machined to tolerances that would have impressed Swiss watchmakers, were aligned using optical instruments. The reduction gears, containing thousands of precisely cut teeth, were assembled in clean rooms that rivaled surgical suites for sterility. Electrical systems snaked through the growing ships like nervous systems. Miles of cable, each wire coded and traced on master diagrams, connected radar sets to plotting rooms, engine controls to the bridge, damage control stations to repair parties throughout the ship. Electricians worked by the light of temporary bulbs, their wire strippers and soldering irons creating connections that would carry vital information through the chaos of battle. The men building these ships understood they were creating something unprecedented in naval history. These carriers would be larger than most battleships, faster than heavy cruisers, and capable of projecting American air power across oceans. Each ship would carry more aircraft than many nations possessed in their entire air forces. The responsibility weighed on every worker who drove a rivet or pulled a cable. As winter approached, the construction pace intensified rather than slowed. Temporary shelters protected critical work areas from snow and ice. Heaters kept metal at workable temperatures. The shipyard operated around the clock, its lights visible for miles along the James River. Local residents grew accustomed to the constant industrial noise, understanding that each hammer blow brought victory closer. The first Essex-class hulls began to look like warships rather than construction projects. Their grey primer coats gleamed under the worklights. Their massive proportions dwarfed everything around them. Visitors to the shipyard stopped and stared, trying to comprehend the scale of what American industry was creating. These were not merely ships. They were floating manifestations of national will, steel embodiments of democracy's determination to survive and prevail. And, by Christmas 1941, as America officially entered the war following Pearl Harbor, the Essex-class construction program had found its rhythm. The industrial machinery of the nation had aligned itself behind a single purpose: building the fleet that would carry the war to Japan's doorstep. In shipyards from coast to coast, the sound of hammers on steel continued day and night, a mechanical heartbeat that would not slow until victory was achieved. The molten steel had become riveted hulls. The blueprints had become reality. The vision of American naval supremacy was taking shape, one rivet at a time, one weld at a time, one perfectly fitted steel plate at a time. Soon, these hulls would feel the kiss of salt water for the first time. But first, they had to be completed, equipped, and prepared for the greatest naval war in human history. The unsung heroes, Workers of the shipyards. The transformation of steel into floating cities required something far more precious than raw materials or advanced engineering. It required human hands, human skill, and human dedication on a scale never before witnessed in maritime history. By early 1942, the shipyards of America had become small cities unto themselves. Newport News, Brooklyn, Navy Yard, Fall River, Philadelphia, Naval Shipyard. Each facility employed tens of thousands of workers who arrived before dawn and departed long after sunset. These weren't just laborers. They were craftsmen, artisans, and specialists whose collective expertise would determine whether America could project power across two vast oceans simultaneously. Consider the morning shift change at Newport News Shipbuilding in the spring of 1942. 28,000 workers streaming through the gates, their lunch pails glinting in the early Virginia sunlight. Among them walked Margaret Chen, one of the first female welders hired by the yard. Her steady hands had already helped seal the hull of USS Essex herself. Beside her, James Murphy carried the tools of a pipe fitter, a trade he'd learned from his father, who had built destroyers during the Great War. Behind them, a young engineer named Robert Martinez clutched blueprints for the complex electrical systems that would soon bring these steel giants to life. Each carrier required the coordinated efforts of over 40 distinct trades and specialties. The hull welders worked in teams of 12, their torches creating cascades of sparks that illuminated the massive construction bays. Above them, crane operators maneuvered sections weighing hundreds of tons with the precision of watchmakers. The margin for error was essentially zero. A misplaced beam could delay construction for weeks, and America's strategic timeline allowed for no such luxuries. The complexity of these vessels demanded expertise that pushed the boundaries of industrial capability. The flight deck alone required specialists in armor plating, a trade so precise that only a handful of men in each yard possessed the necessary skills. These craftsmen understood that the 3-inch steel plates they were installing would soon deflect enemy bombs and cannon shells. Every weld, every rivet, every carefully fitted joint represented the difference between life and death for the air crews who would operate from these decks. Below decks, the work grew even more intricate. The engine rooms of Essex-class carriers housed machinery of staggering complexity. Steam turbines capable of generating 150,000 shaft horsepower, reduction gears weighing over 300 tons, and propeller shafts that had to be aligned with tolerances measured in thousandths of an inch. The machinists who installed these systems worked with the precision of Swiss clockmakers, knowing that mechanical failure in the middle of the Pacific would doom not just the ship, but potentially entire naval operations. The electrical systems presented their own challenges. Each carrier required over 400 miles of electrical cable, feeding power to everything from radar arrays to ammunition hoists. The electricians who installed these systems worked from blueprints so complex they filled entire rooms. A single wiring error could disable critical systems at the worst possible moment. During combat operations, thousands of miles from the nearest repair facility, perhaps no group faced greater challenges than the women who joined the workforce in unprecedented numbers. Before the war, shipbuilding had been an exclusively male domain. By 1943, women comprised nearly 20% of the workforce at major naval shipyards. They faced skepticism, discrimination, and physical demands that would have challenged seasoned workers. Yet they proved themselves indispensable. Rose Martinez, a former schoolteacher from San Pedro, became one of the most skilled instrument installers at the Los Angeles shipyard. Her small hands and meticulous attention to detail made her perfect for installing the delicate gauges and controls that would monitor everything from steam pressure to fuel flow. She worked in spaces so cramped that larger workers simply couldn't access them, spaces where a single misconnected wire could cause catastrophic system failures. The pace of work was relentless. The strategic situation demanded that carriers be completed in 18 months, a timeline that would have been considered impossible just 5 years earlier. This meant 3 shifts working around the clock, 7 days a week. The night shift faced particular challenges, working by artificial light in spaces where shadows could conceal critical defects. Yet they maintained the same exacting standards as their daylight counterparts. Safety in these conditions required constant vigilance. The shipyards developed injury rates that, while high by today's standards, were remarkably low considering the dangerous nature of the work. Welders worked at heights of over 100 feet, surrounded by scaffolding and moving machinery. A single moment of inattention could result in falls that would be instantly fatal. The safety officers who patrolled these industrial cathedrals carried responsibility for thousands of lives every single day. The pride these workers took in their craft went far beyond simple patriotic duty. They understood that they were participating in something unprecedented in human history: the creation of a naval force that would reshape the global balance of power. When USS Essex completed her sea trials in December 1942, hundreds of Newport News workers gathered to watch her departure. Many wept openly. They had poured 18 months of their lives into that vessel, and now she was sailing toward an uncertain fate in the Pacific. The quality control inspectors bore perhaps the heaviest psychological burden. These men and women knew that every component they approved or rejected could affect the lives of 3,000 sailors and airmen. They worked with magnifying glasses and precision instruments, checking welds for microscopic flaws that could propagate into catastrophic failures under the stress of combat operations. Their signatures on inspection reports represented a sacred trust, a guarantee that American sailors could depend on their equipment when facing the Imperial Japanese Navy. The logistics of feeding, housing, and transporting this massive workforce presented challenges nearly as complex as building the carriers themselves. Temporary housing sprouted around every major shipyard: dormitories, trailer parks, and converted warehouses that housed workers who had traveled from across the country to contribute their skills. The cafeterias at Newport News served over 40,000 meals per day, operating continuously to feed workers across all 3 shifts. Transportation networks strained under the load. Special trains carried workers from housing areas to the shipyards, while bus systems expanded rapidly to handle the unprecedented demand. The parking lots at major facilities resembled small cities. Acres of automobiles belonging to workers who had driven from hundreds of miles away to participate in this industrial mobilization. The seasonal challenges added another layer of complexity. Winter construction in northern shipyards required heated enclosures around critical work areas. Welders worked in conditions where their breath froze instantly, yet the steel had to be heated to precise temperatures for proper fusion. Summer brought different challenges. Temperatures inside the hull spaces could exceed 120 degrees Fahrenheit, creating conditions that pushed human endurance to its limits. Despite these hardships, morale remained remarkably high. Workers understood that their efforts were directly connected to the fate of American forces fighting across the Pacific. News from the front lines, victories at Midway, the grinding campaign in the Solomons, the desperate defense of Henderson Field, all reinforced the critical importance of getting these carriers completed and deployed as quickly as possible. The technical innovations developed in these shipyards would influence naval construction for decades to come. Modular construction techniques, where major sections were built separately and then assembled, reduced construction time by months. New welding techniques developed specifically for naval armor created joints stronger than the base metal itself. Quality control procedures established during this period became the foundation for modern naval construction standards. As 1943 progressed, the rhythm of construction reached an almost musical cadence. The sound of thousands of hammers, the hiss of welding torches, the rumble of cranes and heavy machinery, all combined into a symphony of industrial might that could be heard for miles around each shipyard. Visitors often commented on the almost hypnotic quality of these sounds, the audio signature of American industrial power at its absolute peak. The workers themselves developed a culture and camaraderie born of shared purpose and mutual dependence. Experienced craftsmen took pride in training newcomers, passing along skills and techniques that would serve the war effort. Informal networks shared information about the most efficient methods, the best tools, and the subtle tricks that could mean the difference between acceptable work and true craftsmanship. As each carrier neared completion, the pace intensified even further. Final systems integration required the coordination of dozens of specialized teams, each responsible for different aspects of the vessel's complex machinery. The moment when a carrier's engines first turned over under their own power marked a celebration throughout the entire shipyard. Months of individual effort had culminated in the birth of a weapon of unprecedented capability. These unsung heroes of the shipyards had accomplished something remarkable. They had transformed America's naval capability from adequate to overwhelming in less than 3 years. Their calloused hands, their tired eyes, their aching backs, all had contributed to a strategic advantage that would prove decisive in the Pacific War. A symphony of steel, day and night. As the sun set over Newport News Shipbuilding and Dry Dock Company, the first shift didn't end. It simply handed the torch to the second. The great shipyard never truly slept. Arc welders continued their brilliant dance across steel plates, their blue-white flames casting dancing shadows against the evening sky. The rhythmic hammering of pneumatic tools echoed across the James River, a percussion section in an industrial symphony that played 24 hours a day. This was America's wartime tempo, relentless, purposeful, unstoppable. The night shift brought its own character to the yards. Floodlights bathed the massive hull sections in harsh white light, creating a landscape that seemed almost otherworldly. Steam rose from the cutting torches, mingling with the cool evening air. The smell of hot metal and welding flux hung heavy, a metallic perfume that clung to everything and everyone. Margaret Sullivan adjusted her leather welding gloves as she approached Hull 77, what would soon become USS Intrepid. The transition from riveting to welding had revolutionized shipbuilding and opened doors for women that had been firmly closed just months before. Her torch ignited with a satisfying pop, the flame settling into the precise blue cone that would join 2 pieces of quarter-inch steel plating. The war had changed everything about these shipyards, including who worked in them. Women like Margaret had flooded into the yards as men shipped out to fight. They brought fresh eyes to old problems, nimble fingers to delicate work, and an attention to detail that supervisors quickly learned to appreciate. The welding torch didn't care about gender. It responded only to skill, patience, and steady hands. Above her, the massive gantry cranes moved with surprising grace for their size. These mechanical giants could lift entire gun turret assemblies, 40 tons of steel and machinery, and position them with the precision of a watchmaker. The crane operators worked in small cabs high above the deck, their movements choreographed through years of experience and hand signals that had become a language unto itself. The night shift supervisor, Frank Morrison, made his rounds with a practiced eye. He'd been building ships for 23 years. First destroyers in the Great War, then the lean years of the Depression when work was scarce, and now these magnificent carriers. He understood that each shift was a link in an unbroken chain of progress. Miss a deadline here, fall behind schedule there, and the ripple effects could delay a ship's completion by weeks. The Pacific Fleet couldn't afford weeks. Every night brought new challenges. Steel deliveries that arrived with slight dimensional variations, electrical components that didn't quite fit the specifications, machinery that required last-minute modifications. But the shipyard workers had developed an almost supernatural ability to adapt, to find solutions that kept the work moving forward. In the machine shops, lathes turned around the clock, shaping propeller shafts that were marvels of precision engineering. Each shaft was nearly 30 feet long and had to be balanced to tolerances measured in thousandths of an inch. A single imperfection could create vibrations that would shake an entire ship. The machinists who crafted these components were artists in their own right, artists whose medium was hardened steel. The electrical shops buzzed with different energy. Here, women's smaller hands proved particularly valuable for the intricate wiring that would eventually snake through every compartment of these floating cities. Miles of cable, literally miles, had to be routed, secured, and tested. The electrical systems of an Essex-class carrier were more complex than most small towns. Every switch, every junction box, every circuit breaker had to function flawlessly under the stress of combat operations. Dorothy Chen had left her job as a telephone operator to join the electrical crews. The precision required reminded her of the old switchboard work, but the stakes were infinitely higher. A misconnected wire in a telephone exchange meant a dropped call. A misconnected wire in a carrier's damage control system could mean the difference between saving a ship and losing it. The paint shops operated on their own schedule. applying the complex coating systems that would protect these ships from the corrosive effects of salt water. First came the primer, a zinc-rich coating that bonded directly to the steel. Then the intermediate coats that provided thickness and durability. Finally, the top coat in navy gray, that distinctive color that would become synonymous with American naval power. But painting a carrier wasn't like painting a house. The surface area was enormous. Acres of steel that had to be prepared, primed, and finished. The painters worked in sections, following the construction schedule carefully. Paint applied too early could be damaged by subsequent construction work. Paint applied too late could delay the ship's completion. The night air carried sounds from every corner of the yard. The steady thrum of generators providing power to the work sites. The hiss of steam from the heating systems that kept critical areas warm enough for proper steelwork. The distant whistle of locomotives delivering materials to the various construction areas. And underneath it all, the constant rhythm of hammers, welders, and machinery that never seemed to pause. James Wright operated one of the massive plate-bending machines that shaped the curved sections of the hull. The machine could exert hundreds of tons of pressure, gradually coaxing flat steel plates into the complex curves that would give these ships their distinctive profiles. It was work that required both strength and finesse. Too much pressure applied too quickly could crack the steel, while too little would fail to achieve the precise curvature specified in the blueprints. The blueprints themselves were works of art. Thousands of detailed drawings that specified every dimension, every angle, every connection point. The blueprint rooms operated around the clock, reproducing and distributing the constant stream of engineering changes and updates. A modification to the radar installation might require changes to dozens of drawings, structural modifications, electrical routing, ventilation systems. The cafeterias never closed either. Workers needed fuel for this demanding pace, and the shipyard's food service had expanded to match the production schedule. Hot coffee flowed like a river, strong enough to dissolve paint, the workers joked, but essential for maintaining alertness during the long night hours. Safety crews made continuous rounds, checking that proper procedures were being followed. The work was inherently dangerous. Heavy machinery, high voltages, toxic fumes from welding and painting operations. But the safety record had actually improved since the war began. The increased pace had brought increased attention to proper procedures and protective equipment. The medical stations treated the inevitable minor injuries, cuts from sharp metal edges, burns from welding sparks, strains from lifting heavy components. But they also treated something less tangible: the exhaustion that came from maintaining this relentless pace month after month. The industrial physicians had learned to recognize the signs of fatigue that could lead to serious accidents. As midnight approached, the yard took on an almost ethereal quality. The contrast between the harsh work lights and the dark sky beyond created dramatic silhouettes of the ships under construction. These massive hulls, over 800 feet long and nearly 100 feet wide, dominated the landscape like sleeping giants. The security patrols moved through the yards with quiet efficiency. Industrial sabotage was a real concern, and the FBI had briefed shipyard management on the techniques that enemy agents might use to delay or damage construction. But the greater threat came from simple human curiosity. The temptation to discuss the impressive work being done here with friends and family who didn't have security clearances. The workers understood the importance of discretion. They saw the headlines in the newspapers: battles in the Pacific where American forces were fighting with inadequate resources against a determined enemy. Every day of delay in completing these carriers meant more American lives at risk in the combat zones. The night shift brought its own rhythm to the work. Conversations were quieter, the pace slightly more measured, but the productivity never slackened. If anything, the night crews took special pride in maintaining the momentum established by their day shift colleagues. The baton had been passed, and they would not let it drop. Steam continued to rise from the cutting operations. Sparks continued to cascade from the welding stations. The great cranes continued their careful ballet, lifting and positioning the components that would soon transform these steel skeletons into the most powerful warships ever built. This was America's industrial might made manifest, not just in the daylight hours when photographers and officials made their visits, but in the quiet determination of the night shift. the unsung heroes who kept the fires burning and the steel flowing when the rest of the nation slept. And the silent giants take shape. As dawn approached these sprawling shipyards, a different rhythm began to emerge, one of assembly and integration. The massive steel frameworks that had taken shape through countless hours of cutting and welding were ready for their transformation into something far more complex. The carriers were about to become what naval architects called floating cities. And like any city, they required intricate systems within systems. Deep in the bowels of each hull, teams of marine engineers were installing the heart of these vessels, the propulsion plants that would drive them across the world's oceans. The Essex-class carriers required tremendous power. 4 steam turbines generating 150,000 shaft horsepower, enough to push 27,000 tons of steel through the water at 33 knots. Installing these massive turbines was like performing surgery on a giant. Precision work conducted in spaces that would soon be sealed away forever. Chief Engineer Frank Morrison had overseen the installation of turbines on 3 different carriers by 1943. He understood that the engine room wasn't just about raw power. It was about reliability under the most demanding conditions imaginable. "These turbines will run for months without stopping," he would tell his teams. "They'll operate in tropical heat and Arctic cold, through typhoons and battle damage. Every bolt, every gasket, every connection has to be perfect." The turbine installation process required extraordinary coordination. Each turbine weighed nearly 40 tons and had to be lowered through carefully planned openings in the deck structure. Crane operators worked with tolerances measured in inches, guiding these mechanical giants into position, while dozens of engineers ensured proper alignment with drive shafts, condensers, and reduction gears. But the propulsion plant was only one system among many. As the turbines took their places, electricians were threading thousands of miles of cable throughout each ship. The electrical demands of an Essex-class carrier were staggering, equivalent to powering a city of 100,000 people. Every system, from the massive aircraft elevators to the smallest battle station telephone, required reliable electrical power. Master electrician Rose Chen had joined the shipyard workforce in early 1942, one of thousands of women who brought precision and attention to detail that proved invaluable in complex installations. She specialized in the intricate wiring harnesses that would control the carrier's aircraft handling systems, the elevators, catapults, and arresting gear that made flight operations possible. "People think of carriers as floating airfields," Rose would explain to new workers, "but they're really floating factories for launching and recovering aircraft. Every wire we install, every connection we make, it all has to work perfectly when pilots' lives depend on it." The aircraft elevators alone represented marvels of engineering and manufacturing precision. Each Essex-class carrier had 3 elevators, 2 on the flight deck and 1 on the hangar deck side. These weren't simple platforms. They were sophisticated hydraulic systems capable of lifting a fully loaded torpedo bomber from the hangar to the flight deck in less than 20 seconds. Installing the elevator machinery required teams of hydraulic specialists, structural engineers, and precision machinists working in perfect coordination. The elevator wells had to be cut with absolute accuracy. Any deviation would prevent proper operation. The hydraulic rams, each capable of generating tremendous lifting force, had to be aligned and tested repeatedly before the elevators could be certified for operation. Supervisor James Wright oversaw elevator installations across multiple carriers. He appreciated the elegant engineering that made these systems possible. Hydraulic principles that allowed relatively compact machinery to lift loads weighing several tons. "It's all about pressure and precision," he would tell visiting officials. "The hydraulic fluid has to flow exactly where it's needed, when it's needed. There's no room for approximation in these systems." As the internal systems took shape, attention turned to the flight deck itself, the defining feature that transformed a warship into an aircraft carrier. The Essex-class flight deck wasn't simply a flat surface. It was a carefully engineered platform designed to withstand the tremendous stresses of aircraft operations while providing maximum operational flexibility. The deck structure used innovative techniques that balanced strength with weight savings. Rather than solid steel plating, the flight decks incorporated a honeycomb design, steel frames supporting specially treated wooden planking. This combination provided the necessary strength while reducing topside weight that could affect the ship's stability. Installing the flight deck planking required craftsmen with skills dating back centuries, shipwrights who understood how wood behaved under stress, how different grain patterns affected strength, and how proper fastening techniques could create a surface that would endure years of punishing use. Each plank had to be precisely fitted, properly sealed, and secured with fastenings that could withstand the shock of aircraft landings. Master shipwright Thomas Anderson had worked with wood for 30 years before the war brought him to carrier construction. He understood that the flight deck planking wasn't just a surface. It was part of the ship's structural system. Wood has properties that steel doesn't, he would explain to younger workers. It absorbs shock, it can be repaired quickly, and it provides better footing for deck crews. But every piece has to be selected and installed with care. The arresting gear installation represented another triumph of precision engineering. The cables and machinery that would stop landing aircraft had to be positioned with absolute accuracy. The arresting engines, massive hydraulic systems designed to absorb the kinetic energy of a landing aircraft, required foundations that were integral to the ship's structure. These installations couldn't be approximated or adjusted later. Once the arresting gear was in place and the flight deck completed, any modifications would require major reconstruction. Teams of specialists worked with blueprints and measurements that were accurate to fractions of an inch, ensuring that every component would function perfectly when aircraft began operations. The island superstructure, the towering command center that rose from the starboard side of each carrier, presented its own assembly challenges. This wasn't just a navigation bridge. It was the nerve center for flight operations, ship control, and combat coordination. The island had to house radar equipment, radio systems, navigation instruments, and the personnel who would orchestrate complex flight operations. Building the island required integrating structural steelwork with sophisticated electronics installation. Radar arrays had to be positioned for optimal coverage while maintaining the ship's balance and stability. Radio equipment needed proper shielding and grounding. The bridge structure had to provide clear visibility while protecting personnel from weather and combat damage. As these complex systems came together, the true magnitude of the Essex-class program became apparent. These weren't just ships. They were technological marvels that pushed the boundaries of engineering and manufacturing. Every carrier incorporated innovations that would influence naval design for decades to come. The assembly process revealed the extraordinary coordination required to build such complex vessels on an unprecedented schedule. Thousands of workers, representing dozens of specialized trades, had to sequence their work perfectly. Structural modifications that might be simple on a building became major undertakings when they involved a ship's hull. Every decision had consequences that rippled through multiple systems and construction phases. Production managers developed new techniques for managing this complexity. Detailed scheduling systems that tracked thousands of individual tasks, quality control procedures that ensured proper integration between systems, and communication networks that kept all teams informed of progress and changes. As 1943 progressed, the rhythm of assembly became more refined, more efficient. The lessons learned on the first carriers were applied to those that followed. Installation procedures were standardized, specialized tools were developed, and worker teams became increasingly skilled at their complex tasks. The silent giants were taking shape, not just as individual ships, but as proof of America's industrial capability and technological innovation. Each completed system, each successful integration, brought these carriers closer to their destiny in the Pacific, where they would demonstrate the full potential of American naval aviation. A floating city is born. The final phase of construction brought a different kind of precision, the careful choreography of outfitting and completion. While the massive structural elements were now in place, thousands of smaller but equally critical details remained. The Essex-class carriers needed to transform from impressive steel frameworks into fully functional floating cities. Interior spaces that had existed only as blueprints now took physical form. Compartments were sealed and tested, their watertight integrity verified through methodical flooding exercises. Ventilation systems were balanced to ensure proper airflow throughout the ship's 17 decks. From the engine rooms deep below the waterline to the radar operators' stations high in the island superstructure. The galley spaces required particular attention. These kitchens would need to feed over 3,000 men, 3 times daily, while operating in combat zones thousands of miles from any supply base. Industrial-grade ovens were installed and calibrated, steam kettles large enough to prepare soup for an entire air group, refrigeration units designed to preserve food stores for months at sea. Each system was tested repeatedly, ensuring that meal service could continue even during general quarters. Berthing areas presented their own complex requirements. Triple-stacked bunks were installed with mathematical precision, maximizing sleeping space while maintaining minimum clearances for safety. Ventilation ducts snaked between decks, carrying fresh air to spaces that would never see sunlight. Emergency lighting systems were wired throughout, providing backup illumination should main power fail during combat operations. The medical facilities rivaled those of major hospitals ashore. Operating theaters were equipped with specialized lighting and ventilation systems, dental clinics with the latest equipment, hospital wards with capacity for hundreds of casualties. Pharmacy spaces were stocked and organized, X-ray machines installed and shielded, surgical instruments inventoried and secured. These carriers would serve not only their own crews, but also damaged aircraft returning from strikes against enemy positions. Communication systems required extraordinary complexity. Radio rooms were fitted with dozens of different transmitters and receivers, each designed for specific frequencies and ranges. Coding machines were installed in secure compartments, their operators trained in the intricate procedures of naval cryptography. Telephone systems connected every major space aboard ship, allowing instant communication between the bridge and engine rooms, between flight operations and damage control central. The flight deck received its final equipment installations. Arresting gear was tensioned and tested. The massive hydraulic systems calibrated to stop aircraft weighing several tons, traveling at over 100 miles per hour. Catapult machinery was installed and synchronized. Steam pressure systems tested repeatedly to ensure reliable aircraft launches. Fuel lines were pressure tested and certified. Aviation gasoline storage tanks inspected and approved. Aircraft elevators underwent extensive trials. These massive platforms needed to lift fully loaded fighter aircraft from hangar deck to flight deck in less than 30 seconds. Their timing critical during combat operations when every moment could determine mission success. Hydraulic systems were fine-tuned, safety interlocks verified, emergency procedures practiced until they became automatic. Radar installations crowned the island superstructure, their rotating antennas already scanning for targets that existed only in testing scenarios. These electronic eyes would soon track enemy aircraft at ranges exceeding 100 miles, providing early warning that could save thousands of American lives. Radar operators practiced with simulated contacts, learning to distinguish between friendly and hostile aircraft, between incoming strikes and returning air groups. Fire suppression systems received particular scrutiny. Sprinkler networks were tested in every compartment, foam generation equipment calibrated for different types of fires, damage control equipment positioned strategically throughout the ship. These carriers would operate in harm's way, their survival dependent on crews trained to contain fires, flooding, and battle damage while maintaining flight operations. As completion approached, the ships underwent final inspections. Navy acceptance trials tested every system under simulated combat conditions. Propulsion plants were pushed to maximum power. Steering systems tested at flank speed. Communication equipment verified across all frequencies. Each carrier needed to demonstrate full capability before joining the fleet. The transformation was remarkable to witness. Spaces that had echoed with construction noise now hummed with the quiet efficiency of completed systems. Compartments that had been filled with scaffolding and construction materials now awaited their future occupants, ready to support combat operations across the vast Pacific. These floating cities were nearly complete, their steel bones now clothed with the complex systems that would make them the most powerful warships ever constructed. Soon they would receive their crews, their aircraft, their ammunition and supplies. The industrial miracle was approaching its culmination. 24 Essex-class carriers ready to carry American naval aviation to victory. The shipyards had delivered on Roosevelt's ambitious vision, transforming American industrial capacity into instruments of naval supremacy that would reshape the Pacific War. Commissioning and dreams of the open sea. The morning sun cast long shadows across the harbor as USS Essex prepared for her commissioning ceremony on December 31, 1942, the first of her class to officially enter the United States Navy. Her flight deck gleamed with fresh, non-skid coating. Her island superstructure stood proud against the winter sky, while hundreds of sailors in dress whites assembled on her hangar deck for the ancient ritual that would transform steel and machinery into a living warship. Captain Donald Duncan stepped forward to read his orders, his voice carrying across the vast spaces that would soon echo with the thunder of aircraft launches and the controlled chaos of combat operations. The ship's bell rang out, clear and resonant, marking the moment when USS Essex ceased to be merely hull number CV-9 and became a commissioned vessel of war, ready to carry her crew across vast ocean distances toward an uncertain but determined future. Below decks, empty berthing compartments waited in perfect order. Hundreds of bunks with fresh mattresses and crisp linens, lockers standing open like promises of the personal belongings that would soon transform these sterile spaces into homes for young men far from their families. The galley equipment gleamed under fluorescent lights, steam tables ready for their first meals, coffee urns waiting to brew the endless cups that would fuel night watches and early morning flight operations. In the ready rooms, chairs sat arranged in neat rows before blank plotting boards, soon to be filled with mission briefings and tactical discussions, while the ship's library held thousands of volumes waiting to provide escape and education during long Pacific crossings. The sick bay stood prepared with medical equipment and hospital beds, hoping to remain as empty as possible, while the machine shops and repair facilities waited with tools and spare parts to keep aircraft flying and systems functioning thousands of miles from the nearest shipyard. As evening approached and the commissioning ceremonies concluded, USS Essex settled into her berth with the quiet dignity of a great ship at rest, her hull riding easily in the gentle harbor swells, her radar antennas turning slowly in their endless electronic vigil, while her crew began the process of making her truly their own. Across America, her sister ships moved steadily toward their own commissioning dates, each one representing thousands of workers' dedication, millions of hours of skilled labor, and the transformation of Roosevelt's ambitious vision into the floating cities that would carry American naval power across the Pacific. And in the gentle rhythm of the harbor waves against her hull, USS Essex dreamed of the open sea, of distant horizons, and of the vital missions that awaited her beneath tropical skies, where her aircraft would write new chapters in the long history of American naval aviation.